Okay. Good afternoon to everyone. I'm Gianni D'Angelo from the University of Salerno, and I am the chair of this workshop. I'm glad to give a warm welcome to the fifth edition of this workshop titled Cyber Intelligence and Applications, CIA 2027, as part of the International Conference on Computational Science and its applications. I hope you are very well. Organizing the international events has required the help of many people. So I wanted to thank the program committee members and the reviewers for their support. Also, I would like to extend my sincere thanks to you for sharing your work with us in this workshop and for contributing to the quality of the conference program. I remarked that all papers have been peer-reviewed by experts in the specific subject area, and the accepted papers will be published in the Springer Lecture Notes in Computer Science LNCS series, which is indexed by Scopus. Also is indexed is A Engineering, Thomson, and many others index, and several others indexing services. We hope all of you will enjoy this workshop and find this workshop a productive common opportunity to exchange ideas and works about this field of research field. Okay, let's start. I remember that only the video of present speaker can be played. If speaker is not present, his video cannot be played. Anyway, if some present speaker has tech problems, I can play the video. Any speaker has 15 minutes for presentation and just 5 minutes for questions. Please, during to avoid the interference, I suggest all other participants to turn off the microphone during the presentation of other speakers. So the first speaker is Carmine Ambrosino by University of Salerno, and the title of the presentation is Enabling AI-driven cybersecurity through reproducible cloud-native security architectures. By Carmine Ambrosino, Simona Ettari, Alfonso Petrosino, Francesco Bandiera, and Gianni D'Angelo. Okay, the speaker is Dr. Ambrosino.
Okay. Do you see the screen?
Yes, I look here. Yes.
Okay, let's start. Hello, everyone. My name is Carmine Ambrosino, and I'm from University of Salerno. Before starting, I'd like to thank my co-author, Gianni D'Angelo, Simona Ettari, Alfonso Petrosino, and Francesco Palmieri. I'm very glad to present this work today. Let me start with a simple question. If someone presents us both the same model and the same dataset, can we really reproduce a cybersecurity experiment? The answer is typically no. And that's the problem that we address in this work today. This brings us to the issue of reproducibility. In many cybersecurity experiments, many parts are clearly described. The model, dataset is often maybe released, the final metrics are reported, but the infrastructure is often partially specified, and this is a problem. This is a problem because even small infrastructure choices can change the experiment. We can simply consider a reverse proxy that can close all idle connection, or a timeout policy that can limit the effect of an attack, and more. So the infrastructure becomes an hidden variable experiment. And if this is an hidden variable, the experiment is harder to repeat and harder to compare. Our idea today is simple. If you want reproducible AI-based cybersecurity, the environment must be reproducible too. So our work is connected to different research areas, like cyber range, that focus on training, slow dose studies, machine learning studies that focus on model performance, and dataset generation. Moreover, our focus is different. In our work, we connect all these parts, and we don't propose a new type of attack or a new type of classifier. Our main contribution is a fully reproducible experimental pipeline from infrastructure deployment and attack execution to telemetry collection and dataset generation, all the way to AI-based evaluation. In this slide, we present a qualitative comparison, a qualitative overview of different related work. So our goal is not to rank a previous work, but only show some aspects that are important for our study. So we consider four different dimensions, and many existing works usually focus on a specific part of the process. Instead, our work combines all these dimensions in a single reproducible framework. We combine infrastructure as a code, a cloud-native application stack, controlled slow-DOS attacks, telemetry collection, dataset construction, and neural model evaluation. So this table should be read as a qualitative overview of the scientific literature. Let's move on. Our study is guided by 3 different research questions. The first one is about infrastructure as a code. In simple terms, can we rebuild the same lab in a consistent way? The second focus on slow-DOS attack. And the third question is about AI-based slow-DOS detection model. So our goal is not only to create a virtual lab, our goal is to create a complete end-to-end experimental process. To answer all these questions, we developed the local lab. The local lab is a fully reproducible cloud-native security test bed. It is based on infrastructure as a code. In simple terms, this means that the lab is not built by hand. We don't create the machine manually, we don't configure the network manually, and we don't rely on the steps that only one researcher or plus researcher knows. Instead, all the infrastructure, thanks to OpenTofu, is written as a code. In our case, so we use OpenTofu with the libvirt provider. So why OpenTofu? We use OpenTofu because OpenTofu described the virtual machine, network, and the resources assigned to each node. So this is important for reproducibility. And why? For three different reasons. First reason, the infrastructure, thanks to this tool, this automation tool that is a standard de facto, becomes explicit. So the setup is not only described in natural language, but it is described in executable configuration file. So another researcher can inspect what was deployed in our lab, and he can construct different personal lab. Second, infrastructure becomes traceable. Why? Because if we change a timeout, a node resource, a network settings, or a service configuration, all the changes can be tracked in version history. So we can understand which infrastructure produced which experimental result. Third, the infrastructure becomes reconstructable. So the same configuration can be applied again to rebuild the same lab and all workflow. This doesn't mean that every run will be perfectly identical. There may still be differences in hardware, timing, operating system. So we don't claim perfect reproducibility. A better term is controlled reproducibility. We reduce, thanks to this we reduce thanks to this, we reduce all hidden variables. So we make the setup inspectable, traceable, and make change visible. So this is our scientific value of using OpenTofu here. It turns the infrastructure from an implicit background element into an explicit experimental artifact. Now, if we look at the infrastructure, we have 3 different nodes. The first node is target node that hosts the application stack. Nextcloud, ADI as a reverse proxy, and an S3 compatible object storage like MinIO. The second node is monitoring node that collects telemetry of target node using NetData, Prometheus, and Grafana. And the third node is the attacker node, runs Kali Linux and generates controlled malicious traffic. All node runs in the same isolated network, so we can generate attacks, observe the systems, and collect the data in a controlled way. The key point is this: Local Lab does not only deploy machine, it documents the condition under which the security data is produced. And this is why the infrastructure becomes an evidence part of the experiment. So let's look at our end-to-end workflow. The workflow is organized as an end-to-end process. First, we define the infrastructure with Local Lab. And second, we deploy the cloud-native test bed. Third, we generate traffic. We collect benign traffic from normal interaction with the Nextcloud application, and then we execute controlled slow DOS attack. We use 2 different attack scenarios. The first one is slow LORIS that keeps HTTP requests incomplete, so the server keeps connection open. The second is slow HTTP post, generated with the slow HTTP test. Here, the request body is sent very slowly, again, keeping connection open for a long time. Fourth, we collect and process data. We capture packet level traffic using Wireshark and TCP dump. Then we convert pickup file into flow-based feature using NTL Flowlizer, and we obtain slow DOS dataset. So all packet network flow are labeled as normal or slow DOS attack. Then we train and evaluate AI model like MLP classifier, autoencoder-based configuration, and LSTM model. So all the workflow connects infrastructure deployment, attack execution, data collection, dataset construction, and AI-based detection. So this is the core of our proposal. The infrastructure is not just where the experiment happens, it's part of the experiment. Now we look at results, but before we look at the numbers, let's pause for a moment because we were able to repeat all this pipeline multiple times and also on different hardware setups. So this means that across different machines, we could build the same logical experiment, the same node roles, the same network structure, the same application stack, the same monitoring pipeline, and also the same data generation process. Of course, this doesn't mean that hardware differences disappear, but this means that the experimental conditions are explicit and controllable. So again, this is the value of our reproducibility. And Local Lab allowed us to repeat all the experiment. So we let's look at results. All the results shown in this figure should be read in 2 different ways. First, as a comparison of between different neural models like MLP, LSTM. Second, our main focus as evidence that the proposed infrastructure can support the complete process from deployment to attack execution, dataset generation, and more to AI-based evaluation. So we can repeat all end-to-end process on different hardware machine, like all the feature extracted by NTL Analyzer with a mix of feature with a feature reduction with autoencoder, and results. The best overall result was obtained by LSTM model using all the feature set, the full feature set. This is reasonable because low-dose attack are not mainly about traffic volume, they are about time. With a slow behavior, persistent connection, and incomplete request, we catch a slow-dose attack. So our focus again is that all these results are obtained with a different execution on several different hardware. At the bottom, we have shown two different multi-MLP network, neural network, and so we move on to limitations. Because our work has also limitation. First limitation is that the evaluation is based on a specific cloud-native stack. We use Linux, we use a libvirt provider, we test only on Nextcloud, a custom version of Nextcloud with a reverse proxy and a min-IO, so S3 object storage. So different application with different reverse proxy or different timeout policies may lead to different behavior. Second limitation is that the attack diversity is limited. We consider only slow loris, slow post attacks. Future work should include additional attack classes. Third, the Panini workflow is controlled. This is useful for repeatable experiment, but real production traffic is more complex and more variable. The end of limitation, we need more repetition to measure run-to-run variability and provide stronger statistical evidence. So as a future work, we plan to extend this architecture to public cloud platform such as AWS, Azure, and Google Cloud. We also plan to explore Kubernetes-based deployments, multi-platform environments, and more attack scenarios. The long-term goal is to move from local lab to a larger and more realistic cloud-native security experiment. So to conclude, our work presents a reproducible pipeline for AI-driven cybersecurity experimentation. Our main message is clear. Infrastructure matters. It affects the traffic, it affects the dataset, and it can affect the evaluation of AI model. For this reason, the infrastructure shouldn't be treated as an implicit detail. It should be treated as a scientific artifact. With the local lab, we show that a cloud-native security environment can be specified using infrastructure as a goal. It can be reconstructed in a constant way. It can be used to execute controlled slow DOS attack, and it can be used to generate dataset for AI-based detection. At the end, we can also evaluate our AI model, AI neural model. So our contribution is not only a dataset, and it's not only a model. We believe that all this work can help and improve transparency, repeatability, and comparability in AI-driven cybersecurity research. So, thank you for your attention.
Thank you, Dr. Ambrosino. Congratulations for your presentation and for your work. It is very interesting. Are there questions? Some curiosity? Also from remote? No, okay. Dr. Ambrosino, just one question. How did you evaluate the reproducibility of the experiment using your framework?
We evaluate the reproducibility with using OpenTofu. OpenTofu is just an automation tool, but the automation is only part of the point. For us, the important part is to set up that the setup becomes explicit. Without infrastructure as a code, part of experiment may live only in the researcher machine or in the researcher memory, or in AI agent memory. With OpenTofu, the infrastructure choices are written down in a form that can be checked, that can be reused. We can create a different lab with different focus, red teaming focus, blue team focus. So it's not just faster deployment or evaluate. We use that OpenTofu and in general infrastructure as a code represent a standard that that can make the AI cybersecurity research more explicit and traceable.
Okay, thank you. But in your work now, did you repeat the experiment to check the reproducibility?
Yes, all these results are repeated. The first, for example, we repeated for all features in different hardware setup. But for example, the first one result in MLP2 and LSTM in all features are repeated on my machine, on different machine of my colleagues and my co-authors. So these results are obtained with different execution on different machine, and this is true for feature mix and all these results that you view in this group. Thanks to OpenTofu, thanks to infrastructure as a code. So all this infrastructure is repeated on different hardware.
Okay, thank you very much for. There are any questions? No? Okay, thank you very much. Now, the next paper is LADDM, a flexible tool for log anomaly detection by Raffaele Esposito, Francesco Bandieri. So the next speaker is Raffaele Esposito. I'm here.
I'm the presenter. Should I send you my presentation or I can use my computer?
You have the USB pen. You have the presentation.
that time. I mean, is that first
Your name.
no, Jesus Arturo Pérez. Second name.
Okay, LADMA is a flexible tool for model detection. The global scenario showed in last year an increasing of the cyber incidents. The report 2026 shows a clear growing trend. The most alarming thing is that not only the frequency is high, is increased in last years, but also their average severity. In 2024, 77% of incidents are the critical high impact, and in the first half of 2025, this share rose to 82%. In the Global Threat Intelligence Report 2026, we can see that Italy recorded a number of incidents higher than the global average. What is the cost of these attacks?
Sorry to interrupt, you need to share your screen because we can't see this thing.
In the world of graduates.
Yes, of course.
Sorry, thank you. This one?
Yes.
Okay, so it's not on Chrome. You need to go here to Windows and the Edge version. Yeah,
Yeah.
I think now it should be good.
Good. I will check the website.
In the 5 years between 2020 and 2025, Italy, France, Germany, and Spain suffered the losses estimated at 307 billion euros. This situation is alarming, and we must do everything possible to reduce the risk of these attacks. Chandra defined anomalies as patterns in data that don't conform to a well-defined notion of normal behavior. In other words, anomaly detection involving identifying exceptions or deviation for the norm. From the This process is often applied to cybersecurity, fraud detection, predictive maintenance, and the system health monitoring. Identify real anomalies is not easy because often we can encounter false positives or noise, and the balance must be found between identifying too many anomalies, false positives, and failing to identify real anomalies in false negatives. Logs are chronological records of operations performed by users and the system, and this activity is applied to for preventing, for example, unauthorized attempts, cyber attacks, hardware malfunction, or other problems. For this process, we can use different techniques, for example, advanced data analytics, artificial intelligence, and machine learning techniques. This is an example of the system log. And in this slide, we can see a typical workflow of a widely used system based on deep learning approaches. This workflow presents 4 steps: log parsing, log grouping, log representation, and deep learning models. In first step, the log messages are included in the structure template. In the second step, the logs are put into groups with the method, for example, like Windows, or slide Windows, or session-based Windows. In the log representation, log series are transformed in vector numbers. And in the last step, there is the process of where the mega vectors are used to teach deep learning models to tell the difference between the normal and abnormal log tendencies. The 5 most representative deep learning technologies are deep log, log anomaly, play log, log obviously in the CNN. And deep case is an innovative system based on deep learning, deep approaches that analyze in their context. With the goal, the main goal of reducing the workload of operators. Our solution is lab, log anomaly detection program, because it's a system especially oriented to enterprise environment, thanks to its architecture container-based. Lab is a modular system, and in this slide, you can see how works. It works with the well-stacked process that begins with the creation of 2 Docker containers, Docker and Analyzer. Each container has a Docker file with all the dependencies necessary for their operations. LogSim performs two crucial tasks. The first, it generates initial set of logs serve as basis to train knowledge selection models. And second, it generates, simulates an application generated with periodic logs. Lab takes on the role of the model management. It acquires the log baselines and trains the log anomaly detection models, and if necessary, generates new one. The model phase follows. Lab allows to decide to select the range of logs to examine, and then runs the model on these logs. Okay. For experimental evaluation is very important for the models, all system in the all cycle of life. And we choose two complementary types of data sets, a synthetic one and a real one. Using both data sets, we improve the robustness of the analysis. The synthetic data set allows to produce ad hoc anomalies for control the system for in all situations, and each record follows the format action generated 8 bytes from user Y. To verify an anomalous log, each action produces a quantity of bytes that varies randomly. Log is considered anomalous when the volume is n times greater than normal. The HDFS-V1 dataset is a standard dataset using the literature pyramid log anomaly detection techniques, and is extracted from Hadoop distributed system file system logs. It contains millions of lines, and because anomalies are typically generated by system failures or computational errors, this dataset is highly representative of real-world systems. We used 3 models, case version forest and random forest. Once the model generation is completed, we can start with the scanning function of the analyzer. All models available are run in parallel, analyzing one log for several That's it. In this slide, you can see the results of the experiments. This case for synthetic data set not work well. Conversely, isolation forest obtained better results of this case, and the random forest model obtained the best results for this data set. For HDFS V1 dataset, it is obtained better performance than the dataset, and the resolution forest, the random forest, obtained similar results. Characterized by high performance. In conclusion, random forest obtained the best results on synthetic dataset and on for HDFS. Another is very flexible, and its unique feature is and ability to interchange or replace another election models. As a future plans, goal is to make Radmon a fully autonomous tool and integrate Radmon into the business processes and make the key support for data security domains. Thanks for your attention.
Okay, thank you, Dr. Exposito. Thank you for your presentation. Other questions?
Thank you for your presentation. Just a quick question. From the point of view of someone who is developing a software that will emit some logs, it seems like this approach is heavily reliant on how good are the logs, either how verbose they are or how detailed. Did you get any insights on what is maybe the best characteristics for the log messages to be in order to have a good result? Like, should they be heavily detailed? Should they have some keywords or anything that would help?
We affected the log file into web template in a template. In this way, it's possible to record normally log.
I think that the work needs to go other experiments. Okay, it is the primary experiment in the first work in this section. Okay. Okay. Thank you very much. Okay, thank you. The next speaker is Dr. Jesus Arturo Perez Diaz.
Oh yeah, sure.
Yes.
I feel that was shared.
Thank you. It's very good. I'm sorry for you.
No worries. Sorry. I had my own set of headaches with this stuff, so
You have experience this problem.
I work at Microsoft, so
Can I choose PowerPoint or should I choose PDF?
do you have PowerPoint? Right?
Yes, should work.
So actually, it's sharing right now.
It's not sharing this window though. You need to start sharing. I would suggest presenting first.
I to start. Yeah.
and then you go to the.
Yes, it's,
Yeah, it's showing here. Just for you, it's a different view. Is it okay?
okay. You can use the.
If you want the same view, you can open from the PDF. Okay, that's better for you. Because then it will be the same view on both.
Yes, now.
Okay. Is that preferable?
Yes.
Okay, so I then just go to the Chrome browser. So I think it's this one. G. Yeah, then you have to share this. Yes. Window.
Or also inter screen, no?
Yeah, either window
Okay,
or
window. Okay, window.
and this one.
It's better.
I think it
Shape.
also helps that it's in Portuguese. Portuguese. Okay, thank you.
Okay, thanks. The next paper is toward secure and intelligent subject authentication using brain prints and enhanced MAEWEG net. The speaker is Dr. Diaz.
Thank you very much. Thank you very much.
You can start.
Yes, I'm going to present a work that we are trying to use for first time NGNet and brain signals to use or to perform user identification or authentication. In the table of contents, as you can see, we are going to have an introduction used to discuss how do we consider identification and authentication in this work. Also, what about novel biometrics using EEG signals? In this case, how do we perform the process of user authentication and identification, and which was the main goal of this research? Then we will use the methodology, the materials and methods that we use. How do we create or how did we use a data set? How do we perform the EEG data preprocessing of the data set? And finally, the classification models and results or conclusions about user identification and results. Well, as you know, user authentication is, as we advance, is becoming more important because of the attacks that we have nowadays. The number of attacks has increased to traditional passwords in the recent years. And even though multi-factor authentication has been incorporated in many systems, still traditional passwords are the main methods of authentication nowadays. And consider the computational power that we have in these days. We need to have passwords of 12 characters, and almost nobody have long enough and secure passwords nowadays. That's why passwords are vulnerable to engineering or brute force attacks. To mitigate this problem, we can use many different alternatives for authentication. Multi-factor authentication systems are based mainly in biometrics, and we can use fingerprints, iris-based, or even face recognition. However, all these approaches has been found with some issues. For example, in the case of fingerprints, false rejection and spoofing attacks has been made. In the case of iris-based, is in some kinds invasive, and the hardware is also expensive, and it has also some privacy concerns. And with face recognition, even though it's good, it requires always a camera, and it has been some issues with some specific users has been found in these systems. So that's why we are trying to present a different way of authentication. You know that multi-factor authentication systems normally are based on something that you know, like, for example, the password and the PIN. However, both systems are, they present some vulnerabilities, like phishing or credential thief. When you use something that you have, like smart cards, one of the disadvantages is the device loss or the SIM swapping. When you are using something that you are, like biometrics, you can have spoofing or deepfakes or biometric forgery. For that reason, we are trying to present a different way of authentication. We are considering using EGG-based user authentication as alternative for biometric. Which are the advantages? You know that EGGs measure electrical activity in the brain. They are used, or we acquire the signals with sensors placed on the skull, capture the high spectral resolution. We can use different brain responses, like, for example, mental tasks, visual or auditory stimuli. And in this case, we are going to use P300 that use visual evoked potentials. They offer a unique brain patterns, secure and difficult to replicate or steal, enhance a little bit privacy, and reduce the risk of tackling. Yeah, and in this way, we can provide like an alternative or user authentication. So in this case, what we propose is first to define what we call user identification problem. My basically is to extract and predict the identity of an unknown user from the EGG trails of a set of users that are obviously in the data set. Extracting and selecting specific features and pasting the features to any GNet to predict the identity of an unknown user. Basically, the approach that we use to get this is to use a multi-class classifier to classify which specific user it belongs to. And for the user authentication problem, what we try is to verify if one specific user belongs to the claimed identity of one user that it says, I am this user, and we try to verify if that person really is who he claimed to be. So we extract the discriminative features using the MGNet, apply a binary classifier to determine if he belongs to a genuine group or an imposter group, and optimize the performance using FAR and FRR. The motivation is that EGG signals provide highly secure way of user recognition, provide enhanced security using unique brain signals. And normally, brain signals are specific for any person, like any other biometric. And in this way, these EEG signals can provide the identification or authentication functionalities. It can be useful, obviously, in high security environments, like for bank, data centers, healthcare. Obviously, maybe this kind of authentication is not used for daily activities, but for some others that require a more robust security. Well, there are many different works evaluating these studies. However, they have been used many different classifiers, but however, MGNet is one that is dedicated to work with EGGs. That's what we propose this model to make the evaluation of the performance. And we try to discover how is the performance of this model using for authentication purposes, because the previous works they has not been used, sometimes focusing in a specific authentication of users. So the goal of this research was to establish a framework for EGG-based user identification and authentication using the P300 code paradigm, aiming to develop an EGG biometric system, obviously with enhanced efficient user authentication. Well, now, what was the experiment that we did to make the dataset? The dataset was created making this experiment. Basically, is based on ERPs. We had a fixation cross that target the stimuli that they have to pay attention in 1 arrow, then 1 second from preparation, then the stimuli comes, and then arrest. And this is repeated for different times. And we had 3 sessions in different weeks. Once that we have all the 3 sessions, we pre-process, we get the data set, and the data set actually is available. We use a frequency of 256 8 channels, different 16 users or subjects, and 3 sessions that were performed in different weeks. The session 1 and the session 2 were used for training, and the session 3 were used for testing. The users that was included in the experiment, they were volunteers. And once that we have the data set, we make the pre-processing in this way. We use a bandpass filtering from 4 to 18 Hertz. Then we perform the epoch segmentation. Later, we use baseline correction applied using a pre-stimuli interval. Then artifact rejection performed by discarding epochs exceeding plus minus 15 microvolts to ensure a high quality EGG. Then the temporal cropping applied to retain only the post-stimuli interval, the downsampling, and finally the EGG vectorization by flattening each epoch into feature vector. And those were proper for machine learning models and for AGNet. So the description of the entire system is something like this. Once that we capture the EGG signals in the EGG segments, they are pre-processing, then downsampling, then we perform the training, and finally we get the multi-class classification that we want. With this, we consider that we manage the subject identification. Just to know, each class is matched with all or with each subject. And in this way, we had a class for every subject in the experiment. Here is a more detailed part of how this is performed. By basically, we have 3 different blocks to finally manage to have the different classes. And finally, when we want to make the verifications, actually what we do is a binary classification between the user that want to be authenticated. Normally, this user is associated with one specific number. It can be E1 or user 1 or something like this. And we are going to verify once that we get the EGG segments, we are going to perform the pre-processing, the downsampling, and then we are going to verify if that segment belongs really or it matches with a proper class of the user that he or she claims to be. And in that way, with a binary classification, we can determine if the user is genuine what it means that he or she is what he claims to be, or if she or he is an imposter. Then, this is basically how do we perform the user identification. We describe them like a multi-class classification problem. And the final classification layer outputs normally a distribution of all the subjects, as I previously mentioned. And in the user authentication, basically the idea, it was like a binary classification problem where the objective is verified whether an EGG segment belongs to the claimed identity of one specific user. In this case, the model is trained to one versus all, just to make the binary classification. And if we get one, normally we associate it with a genuine user. And if we get 0, we associate it as an imposter. And for that reason, we are going to use a formula with one threshold. And if it is bigger than the threshold, obviously is going to be associated with 1, which it means that he is or she is the user that it claims to be. Otherwise, it's going to be considered an imposter. These are the results of the user identification. Normally, if we have a high AUC bigger than 90, it indicates a strong performance under class imbalance. And as you can see, most of our results were 99 or 1% or 1, what it means that it has a strong performance. There is a low standard deviation that consists that it means that we have a consistent model performance. And in the second figure, we can see that the major or the most of the subjects achieve a 90% of accuracy. Only we have 2 subjects that has a low accuracy, lower than 80%, and 14 users that we had a good accuracy, bigger than 80%. The overall accuracy reached almost 90%, that is very acceptable. And the specific results for user authentications, we can see them in this slide. We have a good sensitive. It's from 80 to 99, which it means that the strong true positive detection. The specificity we have from 93 to 96, which it means a low false positive rate. And we have a compact distribution across all the subjects, which it means a high stability. It demonstrates a reliable, genuine versus imposter discrimination. And also, we evaluated using a GNet with the system subjects, and we can see that the mean accuracy was 89%. The best performance was from the user of subject 3 and 4, where we reached the 100%, and the lowest accuracy was for the user 1, which has only 80% of accuracy. That is considered like an outlier, because most of the users have a better accuracy. So in this way, we can have these conclusions that in case a GNet can achieve a strong performance or manage a good stable accuracy around 90%, it can be considered like a novel contribution, because it's maybe one of the first time that a GNet is used with P300 based EGG biometric authentication. The model demonstrates a good generalization across all the subjects in the dataset, even though the number of users is not as big enough. Actually, this is one of our feature works. The performance variability is used for a few users, and P300 ERPs proved to be secure, not invasive, and discriminative biometric trace. The architecture showed potential real-time applications, and in our future work that actually we are performing it right now, we are trying to evaluate different EGG signals to analyze which signal is better for authentication purposes. So now we have created a different data set, and we are going to perform a deeper analysis with many different kind of signals. For example, we capture EEG signals in REST, another EEG signals performing mental arithmetic activities, another one with ERPs that we study in this first research, and also another EEG signals with motor imagery. And now we are going to compare them to discover which are better for EEG authentication. And well, this is all. Thank you very much. And if you have any questions.
Thank you. Thank you for your presentation. Congratulations for your work. Are there questions? Just one. How do you choose the threshold for binary classification?
Okay. Well, basically, the threshold is defined like around 80%, and it was used previously for previous studies. I mean, if you read related works or the previous related works, there are some papers that had made an analysis just to discover which threshold was like good enough or proper to make that discrimination. So we established that number depending of the previous studies that we had learned from the related work.
You didn't use the AUC curve, the rock curve.
Yes.
Yes. Also, have you used also the curve, the rock curve, to show is the threshold or not?
I think we use it.
Use it. Yes.
Okay.
Another question. Have you tried to use or to add noise in the EEG signal in order to demonstrate the stability and the effort, the strong of the classifier?
We didn't make that experiment. What we did is to consider 3 sessions instead of 2, just to show the variability that they might present from, and the sessions, they were taken in different weeks, more or less with the same time between all the users. They took like the same different time to take from the first session to the second and then to the third. But we didn't add noise with a propose to discover this. How stable is that? But what we noticed that, for example, the user who has a very low performance that were 2, maybe one of the reasons it was that, because maybe one of the sensors on the scalp was not adapted properly, and EGG signals were not recorded properly. So in that way, it can be shown in somehow the experiment that you are asking.
It is an important question because lastly there are the adversarial attacks that use the noise to attack the classifier. So some attacker could use this noise to attack your frame. So the noise is very important. Consider the noise in this work is very important.
Okay, we will
I suggest
yes, for the future work.
You to use and a specific noise, the noise associated with the adversarial attacks.
Okay,
is important.
Okay, thank you very much.
Thank you very much. Any questions? No. Okay, thank you.
Thank you.
The next presentation is okay. Okay, thank you. The next presentation, the title of the next presentation is Analyzing Ensemble Staking Technologies for Supervised Anomaly Detection by Arcangelo Castiglione, Francesco Palmieri, and Antonio Scarfo. The speaker is Dr. Scarfo.
Hi all, could you hear me?
Okay, we hear you.
Okay, let me try to share my screen. Could you see my screen?
I see the presentation, yes.
Okay, thank you, I all. In the next few minutes, I will present this article related to ensemble staking technology in the space of network anomaly detection. The idea, the paper is related to the comparison performance of a team of models, specifically the performance related to staking ensemble compared with well-optimized tree-based ensemble in the space of network detection anomaly. Why we work on that? Because anomaly detection in network space is a core element now for cyber defense, because the attacks related to zero-day are growing a lot. And on the other side, we have a growing, a huge amount of logs coming from the new and the evolving network infrastructure. It's not longer an option to use artificial intelligence and machine learning to analyze this huge amount of logs, and the ensemble landscape need of a reliable reference in this kind of space. What we did. First of all, I said before, we work on combining of models into flavors, homogeneous and integrated framework, specifically random forest and XGBoost. And on the other side, we will compare these strong models with heterogeneous models at two levels of decision, level 0 based on weaker levels, and level 1 with the method that combine the output of the zero level. About the gap we seen time we wrote the article. Basically, again, anomaly detection is a methodology that I used in several spaces, but not so widely adopted in network traffic analysis. And also, we can see that ensembled methodology can improve single scheme, single methodology, but there is a lack of comparison among this ensemble architecture in network anomaly detection space. Again, as I said before, we work on three flavors: parallel aggregation with bagging. Basically, we work on a bootstrap of samples with the correlated space in order to have a methodology that reduces the variance. Boosting through XGBoost, a sequential improvement of the decision of complexity of the methods in order to reduce the error. And as we said before, a two-level staking hierarchical model in order to put together heterogeneous learner and try to exploit the diversity, exploit the benefit, reducing the limitation of the models combined. So Related to zero-level learners, we choose logistic regression, SVM, Gaussian naive Bayes, and decision tree that are heterogeneous methodologies, heterogeneous models, and we aggregate them, combine them through logistic regressions. And then we would, to compare these two-level model with random forest and XGBoost sequential and parallel approach. The scenario is projected in the slide. We have again different ensemble machine learning methodologies in the network anomaly detection space. The task is in the inspection of this kind of traffic through three different scenarios and compare the ability of these three scenarios to detect anomalies in the traffic. The conditions, again, are related to network traffic attacks that basically are really unbalanced. Normal flow outnumber anomalous flow in the real observation. We worked on the four schemes. The most important, the basic schemes, is the first one. I hope that the picture will understandable. The scheme one is the basic scheme, the core comparison, where we compare bagging, boosting, and two-level stacking model given a data set that we will see later. We also try to explore three schemes more. The first one use the meta learner to combine two strong methods, random forest and XGBoost, in order to observe some benefit from these schemes. The third scheme is stacking variance. We use also for the meta learner not just the output of the zero learner, but also in pass-through mode the data from the dataset. And the last for the scheme 4, we use XGBoost methods like a meta classifier in order to understand if this can bring some benefit related to the other schemes. So about the dataset, we started from NSLKDD by Canadian Institute. This coming from a simulated environment, and this is not so unbalanced. In order to improve and assure the state of the art, the network anomaly detection studies, we also had UNSW MB15 created in Canberra. And this is to overcome the limits of artificial nature by data coming from a controlled environment. Also, we try to improve more and use CIC-IDS, that is coming from a Canadian Institute again, and occupies 5 days of realistic traffic. Last two are correctly unbalanced. So we choose these three because we want to assure comparability in our experimentation. Before to do the experimentations, we work on the features, try to reduce the amount, the scope of the features in order to make the model as simple as possible. We did that pruning the feature that were not necessary, and try to find the correlation among features in order to eliminate that feature have a mutual correlation over close to 1 over 2.95 in order to keep just one feature and reduce the number of features. Then we preprocessing the feature, rescaled and normalized the dataset. So in order to provide the experimentation, again, in order to compare the outputs, the performance of the three methods we chose, and define the data set, we did a tuning in order to select the most significant hyperparameters through an exhaustive grid search. We did also a 5-fold cross-validation on the data set training, and like a framework of evaluation, we chose precision recall and F1 score from the confusion matrix for both the classes of the dataset, negative and positive classes. Said that, I'm going to show you the outcomes from the experimentation. The first outcome is coming from the core experimental setup, the benchmark compared the three main ensembles approach, bagging, boosting, and stacking. Stacking that use logistic regression decision tree as WEM and Gaussian base like level 0 learners, and logistic regression like meta learners. We can likely it's not appreciable. It's not. I don't know if you can see the graphs. We go across the three data set and we can see the performance of the zero-level learners on the left side of each single picture, and the last three histograms are related to the performance of random forest, XGBoost, and the stacking. Okay, what we can see across the three data set is that ensemble method consistently outperform the 4-week learners, and the top performers are the stronger methods, so random forest, XGBoost, and XGBoost also had a larger, more imbalanced data set, the last two. The stacking improve, as we said, the individual classifier, but stays slightly in terms of performance below random forest and XGBoost. And we can also appreciate that negative class accuracy is a bit higher because of unbalanced nature of traffic. The second, the experimentation, experimental setup, sorry. We have in this case a logistic regression that combine the output of random forest and XG boosting, and again we can see the first two histogram on the left side that are the prediction random forest and XGBoost, and the last one on the left, on the right side, is the staking output. So we cannot see improvement in staking random forest XG boosting, basically because there are no room to improve these two strong methods. In some cases, hybrid stacks is a little bit different, negligibility different from standalone RF and XGBoost in terms of performance. The third experiments and experimental setups is what we call the pass-through variant. So logistic regression is fostered by decision from the zero learner methods, and also we provide directly dataset information to logistic regression. We did also this approach with random forest and XGBoost stack across the three datasets as usually. We can see that in this case we have not benefit. We have worse results. This is more pronounced when we use weak learners like level 0 learners, and this effect is less evident when we use RF and XGBoost like a zero learner. This effect likely is caused by heterogeneous and redundant information coming from the weak learner that increase the noise and the overfitting risks. The last schemes, the fourth experiments. In this case, we use XGBoost like a meta-learner methods, also in pass-through architecture. For simplicity, I provide the graph across, just one graph across the three. Basically, we don't introduce advantage in this configuration because we have already good performance coming from the XGBoost, and in some cases we also can see some perturbation. So finally, in order to recap, this study try to benchmarking ensemble method machine learning architecture in the specific space in network anomaly detection. Try to use a wide adopted data set. The evaluation was to compare this architecture with this unbalanced data set, and what we can see is ensemble methods remain effective in network in unbalanced data set, and the best performers are random forest and XGBoost. Anyway, stacking that architecture is slightly below, at least in the case of really unbalanced data set. For the future, we have think about several evolution. In my opinion, model distillation in order to have online learning that work on real traffic would be the most interesting. So my presentation is ended, and if you have in time, if we have question, please.
Okay. Thank you very much, Dr. Scarpo. Thank you for your presentation. Other questions? I just one a question. Your results show that the stated ensembles didn't outperform the random forest and the XGBoost, because XGBoost achieves a higher performance. So, does this suggest to you that the staking is a technique that is only beneficial when using where-based learners, or not?
Sorry, I didn't catch the question because I don't hear very well your voice. Could you write down or repeat the question, please?
Yes, your results show that the stated ensemble method do not auto-perform the random forest and the XGBoost.
Yeah.
Is it so?
Yeah.
These experiments, these results suggest that taking method is optimal, is useful only when you use the Waker classifier.
Yes, of course, we have to use Waker classifier, heterogeneous classifier to have improvement, and we stay anyway under the performance of the stronger methods like XGBoost and random forest. Anyway, I have to also say that using these learners, the wake learners, in terms of computational complexity could be useful against the other model. So I think so. I think that.
Okay, thank you. But how does the model handle unbalanced or scarce data?
Sorry, again, I didn't catch how the model handles scarcity of data.
Scarcity, when there are not enough data.
We don't try this kind of scenario. This is why I would try these three methods using real traffic data in order to understand how these three methods behavior in this real case.
Okay, are you planning to extend your experiments in this direction?
I hope so.
Thank you very much, Dr. Scarpone.
Thank you.
Bye. Okay, the last presentation, the title of the last presentation is Optimizing Intrusion Detection for SDN-enabled IoT using of lightweight deep learning architectures by Ali Hamad and Mustafa Saleh. Is online, Dr. Hamad or Saleh? I think that is not online. Okay, I think that is not here.
It seems that's why he just joined.
Standardization.
Chat.
Maybe if you repeat the question, if there is, I mean, somebody entered, it was the one who made come.
Oh, this is the preview speaker.
I think he was trying to enable his microphone, at least from the pop-up.
So, I don't know. Is there,
You just mentioned problem with the microphone.
sorry, the microphone. Okay. But the problem is your microphone.
Yeah, his microphone.
Have you solved it? Not yet. Okay. You can hear our voice, yes? Dr. Scarpo, please. Dr. Scarpo, are you here? Who is? Dr. Scarpo?
Say
So you don't know. It's in Italian all the time. Yeah, so it's the fourth. Dr. Crefon, unshare your presentation, please.
Sorry, are you talking with me?
What?
Ah, sorry.
Unshare your presentation.
I think the person who is the last one of
Thank you.
is Ali Hamad and Mustafa Saleh.
Mustafa Saleh.
And you are talking about the previous one, Scarpo.
yes. No, because he was sharing his screen, the previous guy.
Ah, okay, yeah.
Yeah. Now he left. Yeah. So it's just a matter of the new presenter to be able to talk.
The new talker is the Saleh, Mustafa Saleh. The title of the presentation is Optimizing the Intrusion Detection for SDN-enabled IoT using lightweight deep learning architectures. You can start. Dr. Saleh, you can share your presentation. But is it here or not?
I think it's. Can you scroll the? It left.
Yes, I will. I will. This is the list.
I don't see him. Mustafa.
Yes. There. It's a lead. It's lead. The
Weeks.
yes, sort of the Dr. Ali and Mustafa, or they just come and test their vaccines.
Okay, we can wait or not.
Yeah, maybe we can wait a few minutes. Let's see.
There is some problem.
Yeah, they will always have the same problem.
Same problem.
Yeah.
In other room. Yeah.
Someone online will have their microphone problem.
It's going in and out.
Then we have a few minutes. Yes. We have another time or not? We have to wait, Mustafa.
There are
No.
the minutes.
Okay, I'm sorry, but it's late. Okay, thank you to all the authors for their presentation. All the field is very interesting, and so your contribution is very important for this workshop. And I hope you find this workshop a good container for your research query, research field. I hope that it is a good container of new idea, okay, to explore new research field. I invite you to join the next section, and thank you for all. And now I can declare close this workshop. Can I close?
Yes.
Come si chiama?
Hello, good afternoon.
But the most important research field are the fields and the emails.
Okay.
If you want, send me an email if you want to collaborate with me about this research.
Okay, thank you.
Make the reference to the ICCSA. Remember.
And is your mate here? I think it's not in female. Or you can write.
Yes.
You are in Salerno, Italy? Okay. Where is going to be the venue of next year conference?
Next conference, I don't know now.
Oh, no. So I think last year was in Istanbul, that's right?
No, Istanbul,
But this conference was not.
Conference was going in Athens, in
Last year?
Greece, but Istanbul, not.
Okay.
Is it really good? Yeah. Okay, we leave the room. There are. Thank you very much.
You're
Bye-bye. You're welcome.
Bye.
Bye-bye. Bye.
Bye. Thank you.
Hi, good afternoon. I want to request the chair to kindly start the session. Professor Romaninski. Professor Romaninski, can you hear me?
Yes, I'm here. Yes, I'm here. Can you hear me?
Yes. You can start the session.
Okay. As I understand, you asked me to be the chair.
Yes. Yes.
Me?
Yes, yes.
So let's start our session. I don't see the program, but as I understand, the first talk is of Ali Ahmad, right?
Me. Okay, sure. Yes. Did he take your name?
The
11.
connection is very poor. I hear almost nothing. I do not understand what the problem. Okay, the first talk is the presentation of Elena Gondul. Елена, please start.
Yes, sit here. Yes, so sorry. Sorry. It's okay. Um, um, um,
Just like to say that there are some problem with internet connection with the website of ICCSA. Probably it's no good, but let's start.
Okay. I hope you can hear me. My name is Elena, and I'm going to talk about applicability of neural network called numerical dispersion mitigation neural network to simulate data seismic image from seismograms to obtain precise depth evaluation. So seismic modeling involves finding numerical solution of elastic wave equation in geological domain. So the typical size of domain is 10 by 10 kilometers with depth of 4 kilometers. And the acquisition system or monitoring system located at the surface with zero depth. So, the equation must be solved for a number of sources. That means the number of right-hand sides. So, the typical system has 33 lines with 200 sources. And for each sources, seismic wave field registered by many receivers. And the source density is 60 sources on kilometers in square. So for this system, there need about a month of calculating on supercluster. Because of calculation time of single sources is 30 minutes on the 16 Tesla K40. It's about 4 or 8 GPU hours. So, however, this grid is not sufficiently dense, and specialized require a more accurate data. So it will need need for more fine grid. So if we reduce the mesh by factor of 2, the problem becomes 60 times more complex in three-dimensional case. So for this system, calculation time also increase, and it takes about 500 days on cluster. So the problem has a number of distinctive features. Firstly, there are many sources. That means there are many independent tasks. And the second one, for each sources, we should calculate our equation in subdomain space. So domain cutting many subdomains. So for each subdomain, we use perfectly matched layers to simulate non-reflective wave to obtain physical waves with no reflection, it requires about 130 gigabytes of RAM. So for each subdomain, we used parallel computing to accelerate computational computation. But even using this, the problem is computational complexity. So for the dance, well, coarse grid leads to a numerical dispersion, and if we use a video scheme or order scheme, we obtain such numerical dispersion. It is phase velocity of a numerical solution, and it depends on number of dots per wavelength and current number. So if we compare the velocity with and without numerical dispersion, we can see significant difference. So the red one is the received wave without numerical dispersion, and the blue one is a wave with numerical dispersion. So for researchers, it is not appropriate, and we propose an alternative method to calculate simulations. That's sorry. Using a neural network that approximate transition operation from solution calculated on a coarse grid to solution calculated on a fine one. This approach makes it possible quickly calculate a coarse solution for entire source field, and the training set has a small number of sources. So we train on this training sample our neural network, and the last step is the correction step by training the network. So to demonstrate the quality of neural networks results, we will use a two-dimensional geological environment, geological model, British Petroleum, that has a salt contrast object in center and smoothly changes of velocity in right hand. So the monitoring system has about 3,000 sources with a step of 25 meters, and for each sources there are 512 receivers. For seismic source, we used Ricker with a frequency of 30 kilohertz. So we calculate two sets of seismograms using coarse mesh with 6 meters step and fine mesh with 3 meters step. So if we examine, if we see at the seismograms in detail, we can see that the numerical dispersion has been successfully suppressed. So the first seismogram is a coarse, the second is a fine one, and the third is a seismogram generated by a neural network. The first one is the absolute difference between fine and coarse solution, and the final one is difference between generated seismogram and fine one. So we can see that numerical dispersion is mitigated, but there is a mismatch in amplitude, but it is not. It is not important for researchers and specialists because the phases and the arrival times on the waves for constructing seismic images are important. To obtain seismic images from seismograms, you usually need a processing pipeline that converts raw traces into a reflective image using the Kirchhoff-Prestadt depth migration. This algorithm involves summing the amplitude values along the diffraction hyperbola and placing the resulting value at the point corresponding to the hyperbola's apex. So here on the slide, seismic image obtained from 5 seismogram. Here for using a coarse mesh seismogram. If we look closely at some reflection on coarse one, we see a significant difference here, here, and here. This level of quality is unacceptable to customers. If we look at the difference, we see the numerical dispersion is about 100% in absolute sense. We can see at the generated, and we can see at seismic image obtained from generated seismograms, and we don't see actually such numerical dispersion as we see earlier. So if we look at the difference, we can say that it is acceptable results and acceptable accuracy, but also we have mismatch in the amplitude, but it's not so important. So here I finished my first presentation. If you have some questions, please ask me, or I will continue my next presentation.
Okay. Any questions or comments? Okay. It seems that there are no questions. So, okay. Yelena, please start your second presentation.
Okay. And the next session of my presentation is devoted to extending of this problem to three-dimensional space, and also about some words about training dataset construction. The main challenge is the volume of data. We used for this we used a special procedure using fast Fourier transform. So as seismograms are recorded by at a very dense time resolution, the spectrum of recorded of original signal exceeds Fourier spectrum, and thus high frequency component of the signal is mostly noisy. So we can cut off and take only positive part and 0.3 part of all of the spectrum, and we will work with imagine and real component of the seismogram. So this procedure can reduce dimension of the problem by factor of 5. So we used slightly modified unit architecture as a neural network architecture. This network allows us not only to solve the image-to-image problem, but also to train relatively quickly because of simplicity of the architecture. There are 4 down forward and up forward convolution operation with a 3 by 3 by 3 kernel. So Concatenation are also used to preserve spatial information. So for experiments, we use the acoustic three-dimensional overthrust model. The geological structure of this model is a complex features with a fault located at the center. So the size of the model is 20 kilometers, 20 by 20 kilometers, with a resolution of 25, just three-dimensional model. And the acquisition system uses an area system with lines of with 33 lines of sources with step that allocated 200 meters apart. For each sources, a set of receivers is fixed with a maximum offset of 6.4 kilometers. An important part of our algorithm is the constructing of a training sample that is calculating about 1 or 2% of the total number of sources on a fine mesh grid. However, the question remains as to exactly how to select these sources. So the first method is randomly select the positions of sources. This is a good method as it offers a high probability of covering the entire acquisition system, however, it does not take properties of data into account. So the next one method is equidistant distributively sample. In other words, all sources included in training sample are located. Here is the slide. Allocated at equal distances from one another. This method is better than the previous one as it covers 100% sure the entire acquisition system. And the third one is to use Voronoi diagram, which is in sense combines both approaches. The first step of the algorithm is to randomly select the cluster centroids according to a uniform distribution. Each segment of the Voronoi diagram corresponding to selected centroids becomes a separate cluster. Next, the position of centroids is updated in accordance with the minimization of this functional, where K is the number of clusters, Si is obtained clusters, and X is a vector of source position, and mu is the center of mass of all vectors from cluster. So, to assess the benefits of using our approach, we will carry out some experiments. It has been demonstrated numerically that the error is reduced by a factor of 1.5 for the line under consideration. Furthermore, when using a training sample generated on using the Voronoi diagram, the relative error is reduced by 10% compared with a random and equally distributed sample. Furthermore, if we see at the seismograms, we can see that when an improved sample is used, there is less noise, there is no action dispersion. It is C. However, this the seismic events are of higher quality. That is, there is less numerical dispersion, yes. However, this relatively large error final error is not due to numerical dispersion, but to a mismatch in wave amplitudes following the neural network. So at the same time, for the three-dimensional case, we managed to speed up the seismic modeling by a factor of 12, about 12, for 1% size of training set. Here in the slide, the graph of speed up depends on the size of the training set. So using our approach, you can calculate not 500 days, but 38 days. So I have finished my presentation. If you also have a question, please ask me.
Okay, Elena, thank you so much for interesting presentations. You saved a lot of time. Are there any questions, comments, please? So there are no questions. So probably we can start the third presentation, right?
Yes.
So let me think. Let me see. The third presentation is the presentation of Rafael Cabral de Moura, right? So please. So you can start. The title of presentation is a stabilized finite element framework for transient Darcy-Brinkmann Fauchmer law under local thermal non-equilibrium. Okay, please.
Yeah, can you hear me? The sound is okay?
So,
Hello? Can you hear me?
Yes.
Yes? Okay, thank you. Okay. So my name is Rafael Cabral. I'm located in Brazil now. I'm a petroleum engineer. I will present to you today the work Stabilized Finite Element Framework for Transient Darcy-Brinkmann-Forchheimer Flow under Local Thermal Non-Equilibrium. I'm a PhD candidate at Federal University of Espírito Santo. My advisors are Lúcia Catabriga and Isaac Pinheiro dos Santos, and let's start the presentation. Okay, so this presentation is about numerical simulation of fluid flow through fractured porous media. In particular, the interest here is in high velocity regimes in presence of fractures. So in classical model of simulation of fluid flow in porous media, the work use this Darcy model in the matrix, in the porous matrix, and Navier-Stokes equations and in fractures, and a model that can communicate the simulation between these two parts of the model. And sometimes one model that uses the Darcy model, but with different treatment for those regions. And in this work, we investigate the Darcy-Brinkmann-Forchheimer model that is an improvement of the classical Darcy model. This is because Darcy flow loses accuracy in high velocity regimes and in highly permeable and porous medium, and near of channels and wells, those effects of high velocity and visible effects become more prominent. So a correction for called Brinkmann correction, it's done in model 2, and due to the separation of different velocities of the flow in the fractures in the porous matrix, a separate energy equation need to be used for each phase, for fluid and for solid, to differentiate the temperatures. And the central question here is if we can use a single practical formulation that remains stable across different regimes. In this work, we investigate stabilized equal-ordered finite elements for transient Darcy-Brinkmann-Forchheimer LTNE flow model. The key tools that we use are stabilization methods for finite element, that is SUPG, TSPG, and LSIC. The time advance method is BDF2, and we use to solve the final linear system GMRES with Picard iterations, and the solver was written in Julian language to facilitate the implementation. Okay, so the modeling scope, as I said, I've used the Darcy-Brinkmann-Forchheimer model. That is a type of Navier-Stokes model with a porous drag resistance, with a Brinkmann correction to represent viscous diffusion, and in the Darcy drag we include a Forchheimer correction that is a nonlinear inertial drag. And we include in the model 2 a modification to represent buoyancy-driven convection. And for the energy equations, we use local thermal non-equilibrium to separate temperatures of fluid and solid. In the interface exchange between the two phases is controlled by the Nusselt number, and it provides the ability of the model to represent a lag between the mobile fluid and the temperature of the porous matrix. The target is one coupled model for flow regime transitions without model switching. You don't need to use the Darcy model and Navier-Stokes model and switch between one and other. So this is the equations of the model, the conservation of mass here in the incompressible flow model, the conservation of momentum, here the Brinkmann correction for the diffusion, the viscous term, and here the drag force that has the classical Darcy term and the Forchheimer correction, nonlinear correction for high velocity regimes. And the modification that we have done here for the inclusion of Richardson number to represent buoyancy effects. And for the LT and E, two separate equations for the energy, temperature of fluid and temperature of the solid. Advection just in the fluid phase, with diffusion component by the Prandtl number, and the exchange of energy between the two equations controlled by the Nusselt number. The dimensionless controls that appear in the last equations are the adimensionals, the classical Reynolds number, the Darcy number that is related to the permeability field, the Prandtl number that controls the thermal diffusion, the Richardson number that controls the forced buoyancy, and the interface heat transfer that is modeled by the Nusselt number. Here in this work, we use a correlation of another work that is related to the porous, the porosity of the porous medium, the Reynolds number at the porous scale, that is a modification of the Reynolds number, and the Brundtland number. So when we create the applications, we set the field of porosity, thermal properties, and we classify the flow based on this Reynolds adapted version, Reynolds for porous medium. The stabilized finite element strategy uses this triangular conforming mesh, continuous linear elements for all fields, velocity, pressure, temperature, equal order interpolation that reduces implementation complexity, but imposes some issues that are treated with stabilization techniques. We use SUPG for the advection instabilities, PSPG to treat the equal order interpolation to stabilize pressure, and the SIC to incompressibility residual control. And a key point of this work is the adaptation of stabilization parameters to the model that we are using. So these are the stabilization parameters. This first equation is for the momentum equation, and this second is for the thermal diffusion, advection and diffusion of the fluid phase into the porous media. So the resulting system of equations is a fully coupled transient solver, and the final system of equations is ordinary differential equation. The variable u here is a stacked of unknowns of velocity, pressure, and temperature. And to solve this EDO, we use the BDF2 time stepping method. The nonlinear terms are linearized by Picard iterations, and we solve the final system with GMRS with ILU preconditioning. So to verificate the solution of the numerical solver, we use an analytical fabricated solution that we impose to the equations and solve the system of equations to verify that the solution is recovered at zero initial condition. So this is an example of a parabolic velocity profile and a linear profile for temperature and pressure, and the fields were recovered as expected. And using L2 norms for the error, we can see that the largest deviation is in the pressure as expected for this type of stabilized method in finite elements. So another numerical applications that we bring here is heated cavity. That is a classical numerical application for free flow like Navier-Stokes. So here we bring an adapted version for porous media. A thermal fingers application that is a modification of the heated cavity, but to observe circulation cells with instabilities, thermal instabilities, and a synthetic fractal medium based on a Julia fractal. Each case is evaluate stability and physical consistency for different flow structures, and the results are reported in dimensionless variables. So the first one is the classical heated porous cavity that it consists of a hot wall in the left and a cold wall in the right, and the circulation cell here is a classical solution that was recovered as expected. The second one is the thermal fingers, that is a heated cavity in the bottom and cold wall in the top that make these spheres appear, causing instabilities, but not numerical instabilities. We can see in the solution a symmetrical profile of the solution and could solve it as expected. And we can see here in the top LIC visualization of velocity, we can see the circulation cells for the solution. And the last one is a fractal-based heterogeneous medium that was constructed using a fractal, Julia fractal. We construct the Julia fractal J0 minus I, and take a map with this field normalized and obtain the Darcy field, the Forkheimer constant, the thermal conductivity, and another properties scaled by the profile of the fracture of Julia fractal. And here is the solution. The idea is to use the fractal has a permeability field and another properties, and put an injector here and a producer here. And this shows the velocity solution is a smooth solution, and the pressure solution, no issues in the solution. And the solution for temperature that shows the liquid temperature and the lagging solid temperature, showing smooth solutions too. In the main takeaways that the model Darcy-Brinkman-Forkheimer LTNA can capture porous resistance, viscodiffusion, buoyancy, and two-temperature heat transfer. The discretization with these techniques that we have shown enable robust equal order linear finite elements are presented to be okay to this kind of model. The verification with manufactured solution was recovered without any issues, and the application remains stable even in buoyancy-driven in channelized heterogeneous regimes. And for future works, we use 3D cases, perform stabilization parameter studies, and improvement preconditioning. So I finish my presentation here. I open the floor for questions and comments. And thank you. And spasiba.
Thank you for your presentation. It's really interesting. So, any questions, comments, please? Probably no questions. So, we are going faster than in the program. So let's continue our session. The next speaker is me. I will try to open my presentation. So I shall speak about numerical homogenization of 2D heterogeneous anisotropic porous medium, which is based on a hyperbolic thermodynamically compatible model. This is a joint work with my colleague Lina Reshetova. So you see the presentation?
Yes. Yes.
I hope so. Okay. I continue. So just a brief introduction about the motivations and so on. So the evaluation of effective elastic model of heterogeneous media is of interest in many applied engineering sciences, for example, in the development of new materials with specified properties, in biomechanics, in 3D printing, in seismic exploration, and so on. So the problem here is to obtain the stress-strain relations of an equivalent elastic medium for a complex heterogeneous sample. I have to say that there are a number of homogenization methods, both theoretical and numerical, each of which has its own advantages and disadvantages. In my presentation, I shall speak about a new method which is based on the calculation of the deformation energy of heterogeneous samples and its comparison with the energy of an equivalent elastic medium, and then using a hyperbolic thermodynamically compatible model of the porous medium. The method is based on our previous developments on a hyperbolic thermodynamically model of porous medium. So the general model of a porous medium can be derived based on a combination of the unified continuum model and the hyperbolic thermodynamically compatible multi-phase flow model, which were proposed in recent years. I will not speak about the general model. I just show the model which we used in our computations, which are presented in my talk. So you can see the governing equation for small amplitude wave propagation in a porous medium saturated with a mixture of two fluids, which can be liquid or gas. You see the system here. So you see the equation for the velocities, for the mixture velocities, and for the relative velocities, equation for the pressure, and equation for the stress deviator. Here you see the definition of all variables of coefficients and closing relations. This system is a linear system of PDE, which can be transformed to symmetric hyperbolic form and can be solved by the efficient finite difference method on staggered grid. I just would like to know that these equations can describe the porous medium and also the pure solid and pure fluid. On the left, you see the limiting case of pure solid, which governed by the equation of viscoelasticity. This is the equation of Maxwell linear viscoelasticity. And on the right, you see the acoustic equations. This is simply describes wave propagation in fluid. But this property of the general three-phase model is that we can use diffuse interface approach for simulation of a complex media consisting of the porous medium with inclusions of pure solid and pure liquid. Here is a brief description of the finite difference method on staggered grids. It is a standard method. The details can be found in this paper. And this finite difference method was used to simulation of many test problems. The first test problem is a comparison of theoretically found speed of sounds with those obtained numerically. Here you see the fast compression wave velocity and the slow compression wave velocity and the shear wave. We solved the following test problem. Here is a rectangular filled with a porous medium with a given porosity 0.1. On the left, we generate the wave, and then we compute the velocity of fast and slow wave obtained numerically. It turns out that the numerically obtained wave velocity is a very good agreement with those obtained theoretically. So what we should do if we want to compute the effective elastic moduli with the use of strain and energy method. It's well known that the elastic energy in the volume V is the function of elastic strain tensor epsilon, and it is computed by the following way. There is an equivalent form of energy which can be written in terms of stress. Here is equivalent energy in terms of stress. So what is the main idea to which allows us to compute elasticity moduli? Let's consider the heterogeneous sample. Assume that it is in equilibrium with the following stress field. Sigma 1,1 on the left and on the right is equal to 1, and all other stress components are equal to 0. And if we compute the energy of this sample, we can compute the equivalent elastic energy and can find the compliance stress element S1111. Another compliance moduli can be found similarly. If we want to find all compliance moduli, we have to solve 6 following test problems, and if we solve them, then we can find all compliance tensor. So now briefly say how we solve the equilibrium problem. To do this, we use a time marching method for finding a solution of equilibrium problem. So we apply stress tensor on the boundaries and integrate equations to the time in which the velocities are equal to zero, and it means that we found the equilibrium stress state. And if we compute the energy of this equations, the energy of this system, we can compare it with the energy of equivalent homogeneous elastic medium and find all compliance tensors. So just a couple of test problem. The first test problem is a homogenization of a porous periodic layered structure. Here you see the parameters of the first layer and parameters of the second layer. We applied our method, computed compliance tensor, and compare the result with the classical theoretical estimates, which include classical weight and race bounds, Hill average, and Backus average. From the table, you can see that our numerical values of compliance of velocities, of the pressure velocities and shear velocities are in a good agreement with available theoretical estimates. The second test problem is a numerical homogenization of 2D heterogeneous anisotropic porous media of a complex structure. We computed a compliance tensor for 3 samples with a complex structure. The first is a parallel structure. The second is a parallel structure, but in the angle, but it is rotating on 45 degrees. And the third one is the complex structure of crossed inclusions. So we computed all compliance tensors for these 3 samples, and the conclusion is that for each structure type, the components of effective stiffness tensor are anisotropic for the first 2 samples. Parallel stripes reduces anisotropy. Transversal anisotropy along x-axis. The third sample reduces the same anisotropy but rotated on 45 degrees. And the third sample is the stiffness tensor is almost isotropic. The conclusion is that our method can be applied and for fractured reservoirs in order to estimate stiffness and compliance tensors. So now the conclusion. So we propose a new computational method to estimate effective elastic moduli, which is based on the calculation of the deformation energy for a heterogeneous porous medium saturated with fluid. The method is implemented with the use of hyperbolic thermodynamically compatible model of a wave propagation in porous medium in combination with the diffuse interface method, and it allows us to consider inclusions of pure phases, solid and liquid. To solve the steady state equilibrium problem of polar elasticity, we use time marching to a stationary solution method, which was developed and applied to several test problems. The future work will focus on the improvement of the numerical method for subdomains with large density ratios, investigating the influence of change in microstructure and porosity on effective modeling, and we also want to study the convergence of results when refining the inclusion structure. So the last slide is the reference list. These papers were used as a basis for development of the presented method. So thank you for your attention. If you have some questions, please ask. Okay. No questions. So probably we can start the last presentation. The speaker is Tatiana Khachkova. So Tatiana, please, you can start. Okay, so the next speaker is Tatiana Khachkova. Influence of wettability on electrical parameters based on numerical simulation, results of drainage and imbibition in digital. So please.
Good evening, dear colleagues. Can you hear me?
Yes. Yes.
And presentation is okay?
Yes.
Thank you very much. My name is Tatiana Khachkova, and I am representing our collaborative work. Numerical simulation is now essential in exploration geophysics for estimating rock properties. Traditional lab core analysis is labor-intensive, time-consuming, and frequently leads to sample damage or loss. With X-ray microtomography, we can now construct 3D and digital rock models that accurately replicate real microstructures. These digital twins serve as a realistic basis for numerical simulations. The workflow includes three main stages: scanning, image processing, filtering of high frequency noise, and segmentation, and numerical experiments to compute the properties like porosity, permeability, electrical resistivity, and so on. Various algorithms are now available to investigate the interparameter relationships, the influence of various factors on petrophysical estimates, and to predict of reservoir behavior under changing conditions. Our work employs digital rock physics to investigate how wettability affects electrical parameters during two-phase flow. In hydrocarbon exploration, reserves are estimated from electrical logs using Archie laws. So, accurate determination of Archie parameters, the saturation exponent and the saturation distribution factor, is critical for reservoir planning. The saturation exponent depends on microstructure, wettability, the presence of cement, and pore water salinity. In lab experiments, isolating the effects of microstructure and wettability is very difficult. Moreover, studying the full range of contact angles beyond just hydrophilic or hydrophobic is practically impossible. Yet this is essential because wettability controls fluid distribution, especially during enhanced recovery by imbibition. Additionally, prolonged field development leads to formation hydrophobization. Thus, accounting for wettability changes is critical for reservoir monitoring and production adjustment. This requires novel numerical methods to quickly and reliably determine Archie's parameters as a function of wettability. In our work, we propose a new methodology to refine these parameters. It's based on numerical simulation of steady-state two-phase flow, followed by simulation of electrical current flow. We run a series of numerical experiments to construct the resistivity index versus water saturation for a range of contact angles. This allows us to systematically investigate how wettability affects electrical parameters both during drainage, displacement of the wetting phase, and during imbibition, displacement of the not wetting phase. Our main goal is to derive new functional relationships that improve the reliability of saturation exponent estimates. For our numerical simulation, we use a digital rock sample of benzene sandstone with a resolution of 2 micrometers. First, we simulate primary drainage. The core is numerically fully saturated with water, and only oil is injected to displace water from the rock until irreducible water saturation is achieved. During the experiment, we record the distribution of phases, pressure, and velocities at certain points in time. This gives us a set of models with varying water saturation. For each model, we calculate both the water saturation and resistivity index. Next, we perform imbibition simulation, where the wetting phase gradually displaces the non-wetting one. The wetting phase fraction is an injected mixture. Mixture increases progressively with each imbibition cycle. As in drainage, we compute resistivity index and water saturation for all models. So we got two sets of such parameters. Using these datasets, we solve two optimization problems to construct a linear regression based on both the generalized and the classical form of Archie's law. These figures show resistivity index versus water saturation for drainage, blue lines, and imbibition, violet lines. Solid curves are fits using the generalized Archie's law, and dashed curves the classical form. The methodology for constructing these dependencies and estimating the saturation exponent was described in detail in our previous work. In this study, we applied this procedure for contact angles from 20 to 90 degrees. The left plot shows the results for 20 degrees and right for 60. Thus, for each contact angles, we estimated 3 parameters: the saturation exponent n, the saturation distribution factor alpha, and for these 2 parameters for generalized Archie's law, and the saturation exponent n classical for the classical form. The results are shown on this slide. The left plot with blue markers shows the data for drainage, and the right plot with violet markers shows the data for imbibition. Different markers correspond to different parameters. We found that Archie's parameters depends on the contact angle in a piecewise linear manner. The only exception is the parameter alpha for drainage between 60 and 90 degrees. So we approximated this dependence using linear regression on a logarithmic scale. All other dependencies were fitted with straight lines. The approximations are shown in green for drainage and in yellow for imbibition. To validate these dependencies, we ran additional numerical experiments. We used the same methodology, but with contact angles between the original read points, specifically such values. As before, we calculated the electrical parameters and then estimated Archie's values. These results are shown in figures with red markers for drain and for imbibition. Then we computed the relative errors of our approximation formulas. These approximation formulas and relative errors are summarized in this table. The validation angles are highlighted in red. Most errors are below 3%. Half of them is the 1%, and the rest are between 2 and 3%. Only 5 values falls in the 5 to 10% range. The high errors occurs for all parameters at 86 degrees during imbibition, such errors, and for parameter alpha at 74 and 86 degrees during drainage. For drainage, we initially used a log scale approximation, but a linear fit could also work because the alpha value at 26 roughly extend the trend from the 70 to 8 degree range. So we introduce a piecewise linear correction for 2 intervals, 60 to 70 and 70 to 89 degrees, using the points at 70 and 86, and then validated it at 74 and 80 degrees, which gives errors of 0.6% and 4% respectively. For imbibition, the red markers at 86 degrees extend the linear trend fitted for the 40 to H range. This suggests that linear approximation will hold up to 89 degrees, even through fluid behavior may change near 90 degrees. We applied the correction, and the revised formulas for 86 degrees gave relative errors of 2–3%. On this slide, you can see the table that summarizes the resulting piecewise linear approximations for drainage and for imbibition. And to summarize, our main objective was to determine the dependence of Archie's parameters on contact angle We derived piecewise linear functions with separate trends for drainage and emission. Validation at intermediate angles allowed us to refine the formulas, reducing errors to 3–4%. This new relationship provides a fast and reliable way to estimate electrical parameters under varying variability, which is critical for effective reservoir monitoring and adaptive production strategies. Thank you very much for your attention.
Thank you, Tatiana. Questions, comments? So, no questions, no comments. So, thank you for all participants. Our session is over.
Very much.